Hello, and welcome to this tutorial of the new Generative Fluids workflow, where we will walk you through the picks and clicks of making your own generative fluid study, as well as some of the best practices and potential roadblocks to avoid. For this tutorial, we are going to use generative fluids to reduce the pressure drop through this flow control valve. As of this release in September 2021, the only study you can do in this new workflow is reducing pressure drop. As with most generative workflows, we like to release the functionality as soon as it's ready. So just know that this isn't the long-term vision and that more options will be available in the future, so stay tuned. As you can see from the cross-section, this is a basic hydraulic valve with positions at opened and closed. To start your new study, go up to your Environments dropdown and select Generative Design. You should see a new dialog asking what type of study you want to create. Go ahead and select Fluid Path and then select Create Study. If you don't see this dialog, you can turn on the new generative fluids by going up to your preferences, selecting Preview Features, then scrolling down and checking Fluid Path. The first thing to remember about generative fluids is that instead of generatively designing the parts around the fluid, this study will design the fluid itself. So we start off by editing the model and creating a starting body that represents the extent that the fluid could flow. Here, you see that we use the inlets and outlets to create solids where the fluid will flow into and out of the valve. We then create a cylinder around the valve. Again, make sure this is a bit oversized so the generative algorithm has some material to work with. Once your starting body has been created, we now need to create some areas that fluid is not allowed to flow. The first areas we will create are around the inlet and outlet of the manifold. This is where we will install our fittings, so we can't have fluid shrinking or growing here. Make sure when creating these, you are creating new bodies instead of joining them to the existing starting body. This will allow you to select them separately when setting up your study. After creating these bodies, you are going to create a cap on the outlet. Remember, this feature is in public preview, which means it's not all the way done and there are still some issues to iron out. The reason we need this cap now is if you don't have it, our algorithm will create a mushroom shape outside the manifold and will cause issues with our simulation of the fluid. Last, we are going to create a body right under the valve with a hole the same size as the bottom hole of the valve. This forces the fluid to go through the valve to reach the outlet. After creating the bodies to avoid, we now make our preserved geometry. In this case, we typically make a body for the inlet and the outlet, as these are the bodies you will add your design conditions to. Since this is a simple example, we only have two bodies, one at the inlet and one at the outlet. If you have multiple inlets or outlets, make sure to create a body for each. Now we are ready to define our study. We start by selecting the geometry to preserve. This is the geometry that we just created at the inlet and outlet. We then select the obstacle geometry to avoid. Select all the geometry we made to avoid and then add in the valve. This will force the fluid to go into the top of the valve and come out the bottom. Finally, select the starting body, which is the fluid we modeled. Once your geometry is correctly selected, we now set up our design conditions. This hydraulic valve is rated for 5 gallons per minute, so we will add that condition to the inlet. You will notice that we don't define either the inlet or the outlet. The inlet is any condition that is either a non-zero pressure, a flow rate, or flow velocity. The outlet is any condition with a pressure of 0. This is a pretty common CFD standard that we are using, but we are also looking at adding some more explicit selections to help those not well versed in CFD workflows. So now we go ahead and create our zero pressure boundary condition at our outlet. After our design conditions, we need to define our design criteria and materials. The design criteria is how much volume we will remove while also reducing the pressure drop. For this study, we will set it to 40%. The material is the fluid that you are using. There are two built-in fluids, air and water. But if you have a different fluid, you can use custom and define the density and viscosity manually. In this video, we are using hydraulic fluids, so we will set the material to custom and add our own density and viscosity. This study is ready to run, but I want to show you how the design criteria can affect the outcome of the study. So we will clone this study twice. For the second study, we will set the design criteria to 25%. And for the third, we will set it to 15%. Next, I want to show you how the mesh resolution affects the study as well. We will clone each of these 3 steadies one time and go up to Steady and select Steady Settings. Move the slider all the way to the right to Fine for steadies 4, 5, and 6. Now that you are done, you can see a clipboard with a green check that says our steady has no warnings or errors and is ready to run. Click on the Generate icon next to the clipboard, select all 6 steadies, and then select Generate. This will push these steadies up to the cloud for them to be solved. Depending on the complexity of the steady, this can take anywhere from 20 minutes to a few hours, but since it is on the cloud, you can go ahead and work on something else until it is done. Once the design has been solved, we can select the Explore icon to see all the shapes we generated. One thing you may notice right away if you have used generative design before is that we only have one shape per steady, unlike the structural generative design. This is because so far there is only one criteria we are looking to solve for. As this workflow develops, more criteria will be added, which will then create more shapes per steady. Now that you see the shapes, click on the graph icon up in the ribbon. Switch the y-axis to pressure drop to see how each steady did with reducing the pressure drop while removing material. To show the difference between the fine and coarse mesh that we created, let's hide every steady except 1 and 4. First thing you notice is the pressure drop is much higher in steady 4 than in steady 1. This becomes even more apparent if you select one of the icons on the graph and select the iteration trend in the bottom right-hand corner. If you compare the two, you will notice that steady 4 always has a higher pressure drop than steady 1. This is due to a finer mesh being used to create steady 4, which also makes it a more accurate representation of what's happening. Because the steadies with the fine mesh are more accurate, we are going to turn off steady 1 and turn on steady 4, 5, and 6. If you turn on the iteration trend for steady 5 and 6, you will notice that for these last two, there is a drop in pressure followed by a spike. This is due to the design criteria that we created. This shows that the main driver of the steady is the reduction in volume. What we can take away from this example is to ensure we don't overestimate the amount of fluid we want to remove, as this can produce a result that doesn't get us the outcome we are looking for. This is also an area the team is still working on, as we may want the pressure drop to be the main driver of the steady instead of the volume reduction. Now we can see that steady 4 is the outcome we are wanting, so we can go ahead and click on the outcome view in the bottom right-hand corner to see what the fluid will look like. Here you can also see the pressure variation in the fluid, as well as the velocity through the valve and at the outlet. Once you have finished investigating the steady, you can select Design from Outcome to export the generated shape as a new 3D model. Now you know how to create and analyze fluid flow in the new generative design workflow. For more information on this new workflow, see the link in the description to a blog post by our product manager. If you like this content and want to see more of it, please like and subscribe to our channel.